When performing an optional load calculation for a multi-family building, you have the option to utilize either Table 310.16 or Section 310.15b6 of the National Electrical Code to determine the ampacities of the conductors. Let's delve into each of these options to understand their applications and limitations. Table 310.16 provides ampacity values for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current carrying conductors in a raceway, cable, or earth, based on ambient temperature of 30 degrees Celsius. This table is widely used for determining the allowable current carrying capacity of conductors in various applications. When using Table 310.16, it is imperative to adhere to all the requirements and conditions specified within the table. These conditions include factors such as the type of conductor insulation, the ambient temperature, the number of current carrying conductors in a raceway or cable, and any applicable dirting factors. For example, if the ambient temperature exceeds 30 degrees Celsius, you must apply a temperature correction factor to reduce the ampacity of the conductor. Similarly, if there are more than 3 current carrying conductors in a raceway or cable, you must apply an adjustment factor to account for the increased heat generated by the conductors. These adjustment factors are provided in the notes to Table 310.16. Now let's consider Section 310.15b6. This section provides specific ampacity rules for dwelling unit services and feeders. It permits the use of a higher ampacity for service and feeder conductors in dwelling units under certain conditions. This allowance recognizes that dwelling units typically have intermittent and non-continuous loads. However, there are specific requirements that must be met to utilize the ampacity values in 310.15b6. Firstly, the conductors must be installed in a raceway or cable. Secondly, the raceway or cable must only contain conductors that serve a dwelling unit. Thirdly, the ampacity of the service or feeder conductors must not be less than the rating of the service disconnecting means or the overcurrent protection device protecting the feeder. Furthermore, the ampacity must be sufficient for the calculated load in accordance with Article 220. Section 310.15b6 provides specific ampacity values for copper and aluminum conductors based on the size of the service or feeder. These ampacity values are typically higher than those found in Table 310.16 for the same conductor size. This is because Section 310.15b6 takes into account the diversity of loads in dwelling units. A choice between using Table 310.16 and Section 310.15b6 depends on the specific circumstances of the installation. If you are installing conductors in a raceway or cable that only serves a dwelling unit and you meet the other requirements of Section 310.15b6, you can use the ampacity values provided in that section. However, if you are installing conductors in a raceway or cable that serves multiple dwelling units or other types of loads, you must use the ampacity values provided in Table 310.16. It's also important to consider any local amendments or interpretations of the National Electrical Code that may affect the application of these rules. Local jurisdictions may have specific requirements or interpretations that differ from the National Code. Therefore, it is always advisable to consult with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. In summary, when performing an optional load calculation for a multi-family building, you have the option to use either Table 310.16 or Section 310.15b6 to determine the ampacities of the conductors. Table 310.16 provides ampacity values for conductors in general applications, while Section 310.15b6 provides specific ampacity rules for dwelling units, services, and feeders. The choice between these two methods depends on the specific circumstances of the installation and compliance with all applicable code requirements. Remember to always consult with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. Now, to elaborate further on the practical application of these two sections, let's consider a hypothetical scenario. Imagine you are designing the electrical system for a new multi-family apartment building. The building will have 20 individual apartment units, each with its own electrical panel. You are tasked with determining the appropriate size of the service entrance conductors that will feed the entire building. To begin, you would perform an optional load calculation for the entire building in accordance with Article 220 of the National Electrical Code. This calculation will take into account the anticipated loads from each apartment unit, including lighting, appliances, heating, and air conditioning. Once you have determined the total calculated load for the building, you can then begin to size the service entrance conductors. At this point, you have the option of using either Table 310.16 or Section 310.15b6 to determine the appropriate ampacity of the conductors. If you choose to use Table 310.16, you would need to consider the type of conductor insulation, the ambient temperature, and the number of current-carrying conductors in the raceway or cable. You would then consult Table 310.16 to find the corresponding ampacity value for the selected conductor size. For example, let's say that you are using copper conductors with THHN insulation and the ambient temperature is 30 degrees Celsius. You determine that you need a conductor with an ampacity of at least 400 amps to serve the calculated load. Consulting Table 310.16, you find that a 500 kC rail copper conductor with THHN insulation has an ampacity of 380 amps in a 75 degrees Celsius termination. However, if you use 90 degrees Celsius termination rating, this would increase the value to 430 amps. If you choose to use Section 310.15b6, you would need to ensure that the service entrance conductors only serve the dwelling units in the building and that they are installed in a raceway or cable. You would then consult Section 310.15b6 to find the corresponding ampacity value for the selected conductor size. Section 310.15b6 provides specific ampacity values for service conductors based on the size of the service. For example, a 400 amp service using copper conductors is permitted to use 500 kcmil conductors. This is one example, and it is important to consult the applicable table for the proper values for the specific conditions. As you can see, the choice between using Table 310.16 and Section 310.15b6 can have a significant impact on the size of the conductors required for the service entrance. Section 310.15b6 typically allows for smaller conductors to be used, which can result in cost savings. However, it is important to carefully consider all of the requirements and conditions of Section 310.15b6 to ensure that it is applicable to your specific installation. In addition to the ampacity of the conductors, you must also consider the voltage drop in the service entrance. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause problems with the operation of electrical equipment and can even damage equipment. The National Electrical Code recommends that the voltage drop in the feeder and branch circuit conductor should not exceed 5% at the furthest outlet. To calculate the voltage drop in the service entrance, you would need to know the length of the conductors, the current flowing through the conductors, and the resistance of the conductors. The resistance of the conductors can be found in Chapter 9, Table 8 of the National Electrical Code. Once you have calculated the voltage drop, you can compare it to the recommended limit of 5%. If the voltage drop exceeds the limit, you may need to increase the size of the conductors or take other measures to reduce the voltage drop. In addition to ampacity and voltage drop, you must also consider the short-circuit current rating of the service entrance equipment. The short-circuit current rating is the maximum amount of current that the equipment can safely withstand during a short-circuit fault. The service entrance equipment must have a short-circuit current rating that is equal to or greater than the available fault current at the service entrance. The available fault current is the amount of current that would flow during a short-circuit fault. The available fault current can be calculated using various methods, including the point-to-point method and the infinite bus method. Once you have calculated the available fault current, you can compare it to the short-circuit current rating of the service entrance equipment. If the available fault current exceeds the short-circuit current rating, you must take measures to reduce the available fault current or increase the short-circuit current rating of the equipment. Measures to reduce the available fault current include using current limiting fuses or circuit breakers. Measures to increase the short circuit current rating of the equipment include using equipment with a high short circuit current rating or using a series rated system. In conclusion, when designing the electrical system for a multi-family building, it is important to carefully consider all of the applicable requirements of the National Electrical Code. This includes the ampacity of the conductors, the voltage drop in the conductors, and the short circuit current rating of the equipment. By carefully considering these factors, you can ensure that the electrical system is safe, reliable, and efficient. And remember that the local authority having jurisdiction always has the final say in the interpretation and enforcement of the National Electrical Code. Therefore, it is always advisable to consult with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations.